Thanks again for the organizers for putting this together. I think this has been an interesting experimental meeting, and I think it's the right kind of experimental meeting to bring a bunch of people together to talk about something that maybe none of us really understand. You can certainly count me among those who don't really understand what's going on. And in this case, there's a couple of things I don't really understand. One is depth, and then the other is Szemeredis' theorem, about which I intend to speak today. So my goal for today is to tell you what Szemeredis' theorem is, and then to try to give some accounts of its depth. And if I accomplish those things, that will be pretty good success. So the title of the talk is a quote from French that I'll give you. I'll look at the context of it a little bit later in the talk, but it roughly means lumps of order in an unformed dough. So being French, you're thinking of someone who's working with bread a lot, obviously. And working with the bread, you have a kind of unformed mass, but yet there are lumps of order. This is what Szemeredis' theorem tells us, according to this mathematician. So I thought I'd start by giving you, and so the handout is because these theorems can be a little bit tricky to keep your hands on. There's a lot of quantifiers, so I thought it would be nice to have something written that you could look at as I go on, because the slides will keep moving. But you might want to remember, what did Szemeredis' theorem say? Well, you've got a handout that you can refer to. So I want to start by giving just a bit of prehistory about the result so that we can understand its historical context. The first result I want to talk about is due to Schur. And this is a result from 1916. So Schur argues that you can pick h a positive integer, then there's a positive integer n, depending on h, such that any coloring of the natural numbers up to n by h many coloring, so an h coloring of that set, contains integers a, b, c of the same color, so that a plus b equals c. So nowadays we say that a, b, and c are a monochromatic solution to the equation x plus y equals z. And it's a strange theorem. It's really the first of its kind. There's a result by Hilbert that's not 1,000 miles away, but really this is the first result, and it has a kind of Ramsey theory feeling. And indeed, it's a theorem of what we nowadays call arithmetic combinatorics, but it's before Ramsey. And Schur's interest, he was working on, there was a proof by the University of Chicago number theorist Dixon, who was working on giving a proof of Fermat's last theorem, or at least something in the neighborhood. And Schur was trying to reprove one of Dixon's problems or statements, a theorem, and thought that Schur's lemma would make a nice, or Schur's theorem, sorry, would make a nice way to do that. So it comes out of nowhere. There's no really grand program here that Schur is working with. He's just trying to solve a problem in number theory. But this gives birth to a very large area. So this is a kind of trivial slide, but I want to make sure we're all on the same page. So an arithmetic progression is just a sequence of numbers that progresses in steps of the same size. So for example, 2, 7, 12, 17, these all increase with steps of size 5. And one theorem that came up in somebody's talk yesterday, I think John's talk, was the Dirichlet's theorem in 1837 that if you have two relatively prime integers, then the arithmetic progression an plus b contains infinitely many primes. And that's a theorem in analytic number theory, and I won't really be talking very much about analytic number theory. This is mostly about combinatorial number theory. The next main result in combinatorial number theory is this result of van der Varden from 27. So the result says that now pick h and k positive integers. There's a positive integer n depending on h and k, so that for any coloring of 1 through n by h many colors, there's at least one monochromatic arithmetic progression of length k. So an arithmetic progression of whatever length you want, and it all has the same color. And this is a result that van der Varden says is a conjecture of Baudet, who's a Dutch mathematician hanging out in Göttingen. But there's some reason to think that it was independently conjectured by this Schur, the man we were looking at, who was in Berlin. The proof that van der Varden gives you is a proof using the pigeonhole principle and a double induction on h and k. And this result has been called deep. It's not my subject today, but the Russian Soviet mathematician Kinjin, number theorist and analyst, calls this result deep. And he says that this conjecture was evidently the talk of Göttingen in 27. So when van der Varden comes to Göttingen and solves this, it makes a big deal. According to some historical talk, everyone in Göttingen was working on this Baudet conjecture for a while. The reason that's relevant is that it seems to have been a theorem that was interesting to people, but being mathematicians, there's not a lot of good accounts, at that time at least, of why this was so interesting. But having proved this result, it disseminates its way into Europe, and just a few years later then, Erdish and Turon conjecture that every sufficiently dense subset of the natural numbers contains an arithmetic progression of length 3. So that's that conjecture. So now you can see we're dropping some of the conditions. Van der Varden's theorem tells us that we're going to give an H coloring. We're going to color these subsets of the natural numbers. Now we're dropping coloring. We're just going down to a mere density condition, which I'll explain in quite a bit of detail as we go on today. And the result is that, or the conjecture was that all you need to suppose for a subset of the natural numbers is that it has this sufficient density, and you're going to be able to find within that subset an arithmetic progression of length 3. So that's an infinitary form of the conjecture. Fidetary form, which I like more, just says that so for any delta between 0 and 1, a real number, I'm thinking of it as a density. The conjecture says there is a positive integer n depending on that density, so that every subset of 1 to n of size at least delta times n contains an arithmetic progression of length 3. So this is the first of the conjectures in this important paper by Erdish and Turon. So this is resolved in 53 by Klaus Roth. Is that how we say it? I don't know. Yeah, very good. I have to work on my German. So the theorem is just the conjecture that I showed you before. There's nothing new there. Just pick a density. You're going to be able to find for a subset of n with that density an arithmetic progression of length 3, where n is a function of the density that you pick. It could be very, very big, but just you're going to be able to find for any density you want, there is some n, so that every subset of that, provided it's adequately dense, is going to have this structure. It's going to have an arithmetic progression of length 3. And Roth wins the Fields Medal in 58, and this is listed among the achievements. It's not the only achievement, but it's listed among the achievements for which he deserves the Fields Medal. And the proof is also analytic. It uses Fourier analysis, or what number theorists call the Hardy-Littlewood circle method. I don't really know what that is, but maybe someone here does. So that's apparently an important piece of mathematics. So this was the solution to the specific conjecture of Erdish and Turon for size 3. They also then make a second conjecture, which is that every sufficiently dense subset of the natural numbers contains an arbitrarily long arithmetic progression, not just an arithmetic progression of length 3. So here's the version of what I call the general conjecture. It's also in that same little article from 36. So now you pick a k larger than or equal to 3, pick a density, then there's a positive integer n, depending on k and delta, such that any subset of 1 to n with the cardinality of that subset greater than or equal to delta times n, that will contain an arithmetic progression of your desired length k. If true, this conjecture would entail that the coloring, that structure in van der Varden's theorem was not necessary. It would show that element of the Ramsey theory was too much structure. We can get away with something much weaker, merely density. And again, I'll talk about density in a fairly detailed way shortly. But the idea of density is just, it's a non-zero piece of the natural numbers. Like it's a very weak condition. So this is a pretty strong conjecture. And I guess, to give away the punchline, this is Szemeredis' theorem. So he proves in 1975 the conjecture that I just specified for you. And I've given it again to you in a finitary form. But the finitary form implies, by an argument that I don't want to go over, the infinitary form, which says that every sufficiently dense subset of the natural numbers contains arbitrarily long arithmetic progressions. And that's the form in which you'll often see this theorem cited. Actually, you'll sometimes see it cited in terms of this condition that I found very terrifying at first, even though it turns out not to be. It has a terrifying name, upper Banach density. That sounds scary, but all it says is just you can measure the upper Banach density of a set A by taking the lim sup of the intersection of a subset of the natural numbers with 1 up to n, and dividing the cardinality of that intersection by n. So it measures more or less the percentage of n for a given n that's contained in A. So that's the condition on Szemeredis' theorem. All you need to assume is that if you have a subset that has this density positive, possibly insanely small, nevertheless, it's going to contain an arbitrarily long arithmetic progression. All right, that's pretty shocking. And I want to explain this theorem to you in quite a bit more detail. The reason I've given you the handout is that I don't have the theorem on the slide anymore. But now, as I'm talking, you can keep an eye on the theorem if you want to remember. Why is this what he's saying? So this is the result of Szemeredi. He won the Abel Prize in 2012 for this theorem. So this is the Abel Prize is now Mathematics Nobel Prize. They finally decided that the Fields Medal was not good enough, since you can only get that if you're 40 or younger. So Szemeredi was older than 40 by the time this came up, but he won the Abel Prize just in 2012. And Tim Gowers was invited to give the announcement lecture. So it was just given last week again. The Abel Prize was given to, I think, another Hungarian. And no? Russian, right, Russian, sorry. And a friend of mine gave the equivalent of Gowers' talk, so that was kind of cool. Someone who I would hope would come to this meeting, but did not. So Gowers gives a very nice announcement of Szemeredis' Abel Prize and describes to an audience that's going to consist of just people from, is it Norway? Norway. Here's what the theorem says. So I wanted to go over this because it had a lot of impact on my understanding of what the theorem says. So I'm quoting effusively from Gowers here. So Gowers says the following. He says, one way of understanding Szemeredis' theorem is to imagine the following one-player game. You are told a small number, such as 5, and a large number, such as 10,000. Your job is to choose as many integers between 1 and 10,000 as you can. And the one rule that you must obey is that from the integers you choose, it should not be possible to create a 5-term arithmetic progression. So how can you lose this game? He says, for example, if you were accidentally to choose the numbers 101, 1103, blah, 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 then you would have lost because these 5 numbers form a 5-term arithmetic progression with step size 1002. Now, Gowers observes, obviously you're going to lose this game eventually because eventually you'll just have picked every number between 1 and 10,000. That'll have lots of 5-term arithmetic progressions as you just keep picking. But what Szemeredis' theorem tells us is that even if you had the best possible progression avoiding strategy, you're going to lose this game long before you've chosen every number between 1 and 10,000. So what Gowers is pointing out is that if you're trying to avoid an arithmetic progression of length k while picking numbers from 1 through n for some large n, the largest number of numbers that you can pick is a very small percentage of n, as small as you like, provided that n is large enough. And then so one last bit from Gowers' informal explanation. He says, if, for instance, we are trying to avoid progressions of length 23, Szemeredis' theorem tells us that there is some n, which may be huge, but the point is that it exists, such that if we play the game with n numbers, then we cannot choose more than n over 1,000 of those numbers. That is, a mere 1.1% of them before we lose. And the same is true for any other progression length at any other positive percentage. So I go over this because I want you to have a sense of the astonishment that you ought to have when thinking about Szemeredis' theorem. This is a very strong statement with an incredibly weak premise, simply asking for sets that have positive density, maybe incredibly small. And yet you find that those sets have remarkable structure, arithmetic progressions of any arbitrary length, finite length you want. One quick remark, because I always feel bad giving a talk in which there's not a proof. You can zone out if you don't like proofs, but this is just a short little thing. So I just wanted to point out that Szemeredis' theorem is much stronger than van der Waarden's theorem. In one way in which we can say that is that it implies van der Waarden's theorem. So the proof just goes like this. So given an h and a k, so we're trying to prove van der Waarden's theorem. So given an h and a k, pick your delta, your density, as 1 over h, then run Szemeredis' theorem. That's going to output an n that you know such that any subset A up to n that has its the cardinality of A greater than n over h will have an arithmetic progression of length k. Okay, now pick an h coloring then of 1 through n. Then you know that at least one block, by which I just mean elements of the same color, is going to have its size divided by n greater than or equal to 1 over h. That's more or less a pigeonhole principle argument. But then, just by doing trivial algebra, you get that the size of A is greater than or equal to n over h. And then that means that by Szemeredis' theorem, you'll have satisfied the density condition, and you know that that block contains an arithmetic progression of length k. So that's more or less, that's a pretty simple but convincing enough sketch of how it is that Szemeredis' theorem gets you at minimum this theorem of van der Waarden. Okay. I haven't said anything yet about the proof of Szemeredis' theorem yet, and thank goodness, because this would be another project. So there are three main proofs of Szemeredis' theorem. First, there is the Szemeredi proof, given in '75, for which, as I say, he won the Abel Prize in 2012. And this is a combinatorial proof about which I'll have more to say shortly. Then Harry Furstenberg gave an ergodic theoretic proof in 1977, for which he won the Wolf Prize, which is a prize given by the Israeli Mathematical Union. It was the equivalent, it was the pre-version of the Abel Prize. So he won that in 2006, 2007. And then Tim Gowers gave yet a different proof, a Fourier analytic proof in 1998. And it was, I think, maybe the thing that ensured that he would win the Fields Medal in '98. It was the last major result that he proved. And these proofs go on. Recently, these proofs have been mixed together to yield yet further proofs. So Terry Tao at UCLA has been using a mix of these proofs involving a notion called hypergraphs to get yet further proofs. And typically the aim, ever since Bourgain in 1986, who won the Fields Medal in '94 for his work on Szemeredis' theorem, the goal has been to find better bounds on n. So in the statement I just told you, there exists an n, but it could be really, really large. And a lot of the work that's been done, especially by Bourgain, Gowers, and Tao, have been about trying to get that n smaller and smaller, in part because Erdish had wanted to know information about that. That's not going to be much of interest to me here, but I wanted you to know, if you're wondering, why are there so many proofs of Szemeredis' theorem? It's not just a case of, well, because that's what mathematicians like to do. It's also a case of, there's a specific number theoretic goal, which is more information, more bound information on that number n. Okay, so I want to start segueing into the part of the talk in which I discuss the depth of Szemeredis' theorem. I've tried to tell you what it says and what it means so far, but now, why is it deep? So a first remark is that Erdish seems to have thought so. So Erdish, being a good mathematician of a type I have some familiarity with, talked in terms of money. So he gave, for a lot of his problems, cash prizes, and this one was worth $1,000, $1,000. And Erdish says that I feel that never was $1,000 more deserved. It was the highest amount of money he ever gave, by the way. He says, in fact, several colleagues remarked that my offer violated the Minimum Wage Act. It's kind of clever. So Erdish thought this was amazing. For him, it was worth the most money he would ever give. Since then, finding now bounds on Szemeredis' theorem has generated more cash prizes. So I think now Ronald Graham gives money for improving the bound on Szemeredis' theorem. And I think, so Gowers got more than 1,000, I think, because of inflation. So that was fairly recently. They just keep whittling away at n and winning prizes for it. So Tao wrote a book on additive combinatorics. So there's a theorem of Tao on arithmetic progressions that uses Szemeredis' theorem, for which they won the Fields Medal. And I'll mention that a little bit later. But for now, so he wrote a textbook that's fairly good in the area. They call it additive combinatorics. I call it arithmetic combinatorics, but who cares? So they say, of course, a typical additive set, which think of these subsets of n that I'm talking about. Those are additive sets. will most likely behave like a random additive set, which one expects to have very little additive structure. Nevertheless, it is a deep and surprising fact that as long as an additive set is dense enough in its ambient group, there the ambient group are the natural numbers, it will always have some level of additive structure. The most famous example of this principle is Szemeredis' theorem, a beautiful and important theorem. So I wanted to, this is just supposed to be the sociological data saying, yes, mathematicians consider this deep. I now want to try to give you 4 different types of accounts of its depth because I want to try to make sense of this. So I call these genetic views, evidentialist views, consequentialist views, and cosmological views. I just wanted to, it's fun to come up with these names. It's like one of the best things of being a philosopher is you get to make stuff up. So if you think these names are stupid, I'm very open to less stupid suggestions. Except for this one, which I think is really nice. So the others just whatever. So I'm open to improvements. All right, so first maybe the silliest of them, but it's one that's come up in various ways. It's what I call a genetic view. And the first observation is that when we're talking about depth, mathematicians want indicators of depth. And a typical indicator is the talent of the mathematicians who prove the theorem. So for instance, you get this paper, a recent paper by Zeilberger, who says the depth and mainstreamness of this deep theorem, he's talking about Szemeredis' theorem, can be gleaned by the fact that at least 4 Fields medalists, Roth, Bourgain, Gowers, and Tau, and at least 1 Wolf Prize winner made significant contributions. And I thought that, even though this is I think fairly silly, but it's still worth considering, you could try to convert this indicator to a criterion for depth by just saying that a deep theorem is one proved by sufficiently talented mathematicians. And we could call that a genetic view of depth. I don't think many of us are going to be very persuaded by that. I mean, for one thing, that strikes me as it's a relatively subjective view. I'm sure we can find some jerk out there who wants to trash this work and just say that it's worthless. Maybe that's putting it a little strongly, but it's a big world. The second point is that I take it that the trivial theorems of big-time mathematicians then would also count as deep. And that doesn't sound so good. So I wouldn't be thrilled about saying that this is the main criterion of depth, but it's out there, and I wanted to at least bring it to your attention. And it's out there in the literature on Szemeredis' theorem. All right, so I think maybe a little bit more interesting are what I want to call evidentialist views of depth. And these are the views that say that the depth of a theorem is related to the quality, some quality of its proof or its proofs. And we've talked about this yesterday. All these ideas were suggested to me just by going through the literature. And so in the announcement of Szemeredis' Abel Prize, they give what I take as a kind of evidentialist application. Many of his discoveries, Szemeredis' discoveries, carry his name. One of the most important is Szemeredis' theorem, which shows that in any set of integers of positive density, there are arbitrarily long arithmetic progressions. Szemeredis' proof was a masterpiece of combinatorial reasoning and was immediately recognized to be of exceptional depth and importance. So they call the proof a masterpiece. They call the proof a masterpiece. The theorem is important, but the proof is what is deep. And this is, I think, a view you will often find in the literature when people talk about depth. I'm just focusing on Szemeredis' theorem because that was enough to look at. But you find this kind of talk, in particular in number theory, quite often. So a text that I've been looking at for a long time for some reason I don't really understand is a text by a mathematician named Daniel Shanks. This is a problem called Solved and Unsolved Problems in Number Theory. I don't even know if this is an important book. He was a guy who worked for the Naval Research Board, and then I think was an adjunct professor at Maryland for a long time. So I don't know, but this book, for some reason I keep running into this book. And he has this at least vivid passage on depth in which he says that we confess that although this term deep theorem is much used in books in number theory, we have never seen an exact definition. In a qualitative way, we think of a deep theorem as one whose proof requires a great deal of work. It may be long or complicated or difficult, or it may appear to involve branches of mathematics, the relevance of which is not at all apparent. So he's lumping a lot of stuff together. I take it we could try to classify these as statements that the depth should be located in either the laboriousness or the impurity of its proof. So let's just think about those a little bit. So as far as its laboriousness goes, this is awesome. This is a diagram in Szemeredis' paper, the 75 paper, On the second page, he says, I've given you a flow chart for my proof. I love that. I wish more mathematical papers had this kind of diagram. So you can see, I mean, so here's Szemeredis' theorem, it's T, and all these other pieces are the individual lemmas and facts that he assembles in just the right order to prove the theorem. Just to observe, he uses van der Waarden's theorem to prove Szemeredis' theorem, which is fine since it implies Szemeredi implies van der Waarden. You get this cool pentagram structure, right? It's like, I don't know, I thought this was...
You get out once you get in?
Yeah.
There's an if and only if between the T and
I didn't say sorry. Right.
Yeah, one text I looked at pointed out that from this diagram, it's actually non-trivial to check that it's actually valid. Like, try to follow the arrows and make sure that there's no circle in here. Not trivial to do that, even just from the diagram. So that's his proof in a beautiful overshell or over.
It's weird that these F's, the facts feed into the definition.
Yeah, yeah,
Are some of those dotted lines and some of them solid lines?
yeah, they are.
Some other kind of line in there?
I think that the dotted lines are steps that he doesn't use, but that he could use. So you see, he goes from this. Oh no, I guess. Yeah, that can't be right. Or maybe it's that it's optional. You could go here and do it, or I don't know.
Exercises for the reader.
Yeah.
or maybe there are several choices and you happen.
That's what I think. He doesn't explain the diagram. And he says that he sat down with some friends and they concocted this diagram before he published the paper because he wanted it to be, he knew that the proof was really hard. So I present this both because it's beautiful, but also because I wanted to convince you that yes, the proof is laborious. So it meets Schenk's criterion. I mean, you can have a look at the paper. It's about this hard to read. Well, yeah, maybe not. So one of the statements in here is the so-called Szemeredi regularity lemma, which we'll talk about later, and that alone is a theorem that has had vast consequences in machine learning. So it's sort of along the way he solves like a completely different kind of problem, just to get this theorem. But I'll talk about that in a minute. So clearly, I think you can accept that it is undoubtedly long, complicated, and difficult. I think that's undoubtedly true. On the other hand, it's widely been judged elementary, which is to say, as Gowers puts it, it does not make use of advanced concepts or rely on previously established difficult results. And that's because the proof is in fact pure. It's purely combinatorial. There aren't any appeals to analysis or anything like that. It's just a masterpiece of combinatorial reasoning, of a combinatorial theorem. And so without getting into a long discussion of purity, I don't want to do this morning, it satisfies, at least on a rough understanding of what a pure proof is. It draws only on concepts and definitions and so on that are contained within the problem or theorem that you're looking to solve or prove. So that means that this proof then would be deep on one but not the other of Schenk's evidentialist criteria. And it's not clear to me, I mean, not that we should necessarily care much about what Schenk's had to say, but it's not clear to me if we were going with what I'm calling an evidentialist criterion of truth, which of those two is more important for depth? Is it better that the proof be laborious to make it deep, or is it better that it be impure? I don't know. That's the problem when you get these sort of smorgasbord of options, right? Which one do you choose? For the philosopher, this is going to be important if we think we can give a criterion of depth, unless we just judge that it's actually a splintered concept. Maybe is the right situation. So I wanted to raise one other kind of problem for thinking about these evidentialist criteria before I turn to yet another criteria. So the other situation is that if we're thinking about depth as measured by proof, the problem is that there are lots of different proofs of Szemeredis' theorem, as I showed you. And for instance, the Szemeredi proof is pure, but Gowers' proof is analytic. It's not pure. It uses Fourier analysis. That's why he wins the Fields Medal. It's like, wow, cool. You can use Fourier analysis to solve problems in combinatorics. This is Gowers' whole shtick, right? Combinatorics is at the center of mathematics, and analysis is really just a tool for combinatorics. You could fix this, I suppose. I mean, we could start doing some of the kind of epicycles like we were doing yesterday afternoon. So you could think that a theorem is deep if some of its proofs are impure. But that's not a good idea. I mean, you could just easily insert some extraneous impurity into an otherwise pure proof. And you'd want to have some answer to the question about which impurities are somehow essential to a proof being that proof. You'd need, as I was trying to mention yesterday, a criterion of individuation of proof. That would be great. I don't have anything like that. You could also do something like count a theorem as deep if all of its proofs are laborious. On the other hand, laboriousness is a funny criterion. I mean, you were thinking that maybe that proof wasn't so laborious, right? So that's a fairly contingent or subjective criterion.
Are any of the
Yeah.
proofs insightful?
I think most people don't think Szemeredis' proof is insightful. When people when they say you'd like a proof of, if you want to see the proof, they turn you to Furstenberg's proof. So this is the ergotic theoretic proof that has been of interest to logicians recently. So Jeremy Avigad has been doing some proof mining of that proof.
And what about Gower's proof? Is that insightful? Or what was the
Gower's, in fact, in his paper, it's funny, the paper in which he does this, he says, I'm going to give you a proof, but it's not self-contained, he says. If you really want a nice self-contained proof, he says, go read Furstenberg. And then he goes on and he does his thing.
So what was his justification for doing that?
He uses analysis. So he wanted to show that these techniques of Fourier analysis are, and in fact, that's not,
So good it can prove it from point to point.
it's not so really, so I mentioned to you earlier that this guy Roth had given a solution to the Szemeredi theorem in just case 3, k equals 3. And that's an analytic proof. And what Gowers does is he just uses that proof and shows that it can be extended. Nevertheless, it's still a major accomplishment, in part because it set a lot of the agenda of number theory since then. So for instance, almost all of Tau's work comes in that tradition of using analytic methods to try to solve problems in combinatorial number theory. Okay, so I wanted to say that all these currently known proofs are laborious, but it's hard, as a philosopher, I don't want to settle on that. So, you're just throwing out a few more possibilities. So other evidentialist strategies would say that a theorem is deep if its shallowest proof is deep, with some notion of shallowness, or its simplest proof is deep, some notion of simplicity. Shortest proof, using, I guess, something like proof theory. If we wanted to get all Frege, we could talk about its canonical proof being deep, or proofs from the book, or whatever you wanted to talk about, yeah. Every proof of it is deep. Every 80% of its proofs are deep. I don't know. I mean, once you open up the evidentialist can of worms, these are the kinds of options that are on the table. As I see it, the problem is that they're all parasitic on a prior notion of depth of proof that we don't have. So, I mean, if you guys want to have another conference like this, and instead of talking about deep theorems, talk about deep proofs, then that would be one way to sort of begin this project. But if we're thinking just about depth of theorem, this is more just like a retreat. And they also depend on this very problematic idea of how to individuate proofs. All right, so let me move on to the third type of deep proof, or deep theorem that I had in mind, criterion for depth. So these are what I call consequentialist views of depth. And here's where we measure the depth of a theorem by some quality of either its consequences or of the consequences of its proof. So for instance, when Gowers talks about Szemeredis' theorem in the Abel Prize announcement, he singles out its applicability to other areas of mathematics as one of the reasons why it's fascinating. The theorem is useful for areas. And one of the things he has in mind is this famous result of Green and Tau that I mentioned earlier. So they use Szemeredis' theorem as one of their premises to prove that there are arbitrarily long arithmetic progressions that consist only of prime numbers. So this is a Fields-Medal theorem, the main item in Tau's Fields-Medal announcement. And Szemeredis' theorem is the key to that. So that's one instance of what Gowers has in mind when he says that look for a quality of the consequences of it. If it's fruitful in some powerful way, then it's deep. Relatedly, you could look at what I call a consequentialist account, focusing, as I say, on the consequences of its proofs. So as I mentioned to you earlier, one key step of the proof that Szemeredi gives is what's come to be known as the Szemeredi regularity lemma. This is, as he says, it's a structural classification of large graphs. And this has become a central tool in graph theory and also, as I was mentioning earlier, theoretical computer science in the problem of machine learning. It's apparently very central in that area of computer science. So that's the proof. The proof gave birth to this vast application. And that's one reason to think that it's deep. Right. I'm just walking you through the smorgasbord at this point. I hope I'm not overwhelming with too much good food. So one last comment about these consequentialist views. So these views are interest dependent, I take it, as we talked about yesterday, that a theorem is deep only so long as these consequences are of interest to us. And this, again, threatens to make depth subjective. But I suppose, depending on how you swing, you might take a Platonist or Kantian view and say that, in fact, our interests are not subjective, but they're grounded in some feature of the cosmos or rationality or something. If you go that way, then you might be very favorable to a consequentialist account of depth, since the theorems that are going to have important consequences, that's a determinate fact because of some objective feature, whether it be an objective feature of our thought or of the world as a whole. I'm pretty neutral on that position. I think it's not what I'm trying to advocate, because the view that I find of the smorgasbord the most interesting is the last one, is what I'm calling a cosmological view of depth. And I chose this word because it comes from the Greek word cosmos, which means order. And so here's where, this is the passage from which I took the quote that I gave to this talk. So this is a member of the CNRS at Jussieu. He wrote a book that's a kind of a popular math book. It's Mathematics, an owner's manual. It's kind of nice text. And so he writes, this is my translation, he says that Szemeredis' theorem is a deep combinatorial result that establishes, like Ramsey's theorems, the inescapable presence of certain structures, lumps of order in a formless dough, even though we have a great deal of freedom of construction, since the only constraint imposed on A is positive density. Okay, and you find, I think, a fairly similar view of Szemeredis' own view of what he did. So this is in an interview he gave after winning the Abel Prize 2 years ago. He says, in finite objects, we look for patterns, different shapes, and try to understand what conditions make different patterns emerge. This is one of the fundamental questions. A slightly pompous and philosophical way to put it, aren't those identical? Why didn't it's redundant, yeah. Is that we want to prove that there is order in any chaos. In other words, if you give me a hostile structure, I will still be able to find orderly parts in it. And this is what he thinks Szemeredis' theorem does. It reveals order in chaos, lumps of dough, lumps of order in a formless dough. So I want to try to run with this a little bit, really little bit, I guess only 3 slides. But this is the one I find the most intriguing of these accounts. So what Szemeredis' theorem tells us, recall, is that any arithmetic progression of length k, any desired positive density, there's an n such that we are guaranteed to find such an arithmetic progression, choosing only from a subset of 1 to n of our desired density. So the size of that subset can be very small relative to n. And so I take it that what Godefroy calls a formless dough, what Szemeredi calls chaos, are these chosen dense subsets of 1 to n. Because we choose these subsets without any constraints. All we do is choose a subset of positive density. And yet, what Szemeredis' theorem shows is that these randomly chosen sets must contain arithmetic progressions of the desired length. They have very strong additive structure, despite the fact that the choice we made was random, and the only condition was just that these sets have positive density. No reason to expect any such order, and yet you get that order. That's what Szemeredis' theorem tells you. And so I want to say that this unexpected structure is what makes Szemeredis' theorem deep, at least on what I'm calling a cosmological view of depth. So to say a little bit more about this idea, the idea is that there is serious structure latent in the premises, despite their evident structural weakness. The premise here being simply the positive density. Now, the way I put it is, as we saw in the discussion yesterday, to call the revealed structure unexpected makes it sound like depth depends on our ability to expect or to see structure. And that, if that were true, if the depth of a theorem simply amounted to our inability to recognize order, then depth would be rather subjective. So I thought it could be helpful to consider a kind of very preliminary approach to trying to make this a little bit more precise. So these are, any precisification distorts, but maybe can shed a little bit of light. So here's the idea. So suppose there's a predicate S that measures the order expressed by a statement. I mean, right there, a lot of you are just going to get off the boat, right? I'm just saying, suppose there is such a predicate. But we can at least treat this thing sort of formally. So the way of talking about it would be to say that a theorem is cosmologically deep if that predicate, the order expressed by the premises, is much less than the order expressed by the conclusion. And there's at least a couple of ways you could go here. So S could be measuring the orderliness of the entities specified by the statement. So in particular, looking at these, what I was calling random subsets of n of positive density, you could look at those sets and talk about try to measure their orderliness in some precise way. Or you could think rather of somehow the state of affairs specified by a statement. So in other words, plug in the actual premises, as it were, try to measure the orderliness, not of the entities, but rather of the propositions involved, or the statements involved, depending on how you swing that way. So those are a couple of ways you could begin to try to cash out S. And we were playing around with this a little bit this week, and my colleague Balázs Guinness, who's met Szemeredi, that was kind of helpful. So he observed that if we just put very weak coding conditions, so we talk about trying to apply S, take the premises to be coded by Gödel numbers in a normal way, usual way. If we, and suppose just a few very weak things, if S is a total computable function such that S is invariant for logically equivalent statements, meaning that if two statements are provably equivalent, then they have the same orderliness according to S. If you have those two conditions, then it follows that there could be no deepest theorem. That's actually not that surprising. Why should there be a deepest theorem? So in fact, he just observed that these three conditions, totality, invariance for logical equivalence, and deepest theorem, they're mutually exclusive. They can't all three be satisfied. Just an interesting observation. So you can already begin, this is a proposal that has enough form that you could begin to do something with it. Maybe if I had another few weeks, I might have said something more about that. But
Aren't all true statements logically equivalent? Or do they have different?
no, so I mean, so actually what I really want to say here is provably logically equivalent. So I want provably equivalent.
If they're true, then they're provably.
No, so within, say, arithmetic, for instance, so we could relativize all this to say within piano arithmetic and just talk about two statements as having a proof of their equivalence within that formal theory. So two statements, lots of statements won't be equivalent under that condition. So pi1 statements won't be equivalent to lots of pi2 statements and so on. So I recognize the point, and by putting it in terms of logical equivalence, I do suggest that. So I want provably equivalent relative to some fairly weak base theory. But good question. Also, I have no idea how to build S. As I was telling you, maybe you just get off the boat immediately. But so I can't even tell you whether Szemeredis' theorem is deep on this view. I also don't know whether it would be plausible that every agent of our rational type would judge the extension of S in the same way. As it came up yesterday, suppose we ask, how would God perceive the depth, or in particular the orderliness of a statement? Maybe our perception of orderliness is somehow merely a function of our particular rational type, or even something more specific to our individual nature. I don't know. Just it's an idea. So this is a potentially promising line of investigation. Taking a little risk here, but this is, I think, a different idea of how you might think about depth that might have some legs. To me, it seemed, I like this cosmological idea because it focuses on just the statement. You're not thinking about proofs. You're not thinking about consequences. You're thinking about what a theorem says and how does the world look according to this theorem. And that its depth consists in the imbalance between the world as it appears in the premises and the world as it appears in the conclusions. And I want this to be not epistemic. I want this to be something more objective than that. So I gather that the faith of Szemeredi and of this and Godefroy is that there is something more objective there. But hey, I'm just waving my hands at this point. So let me wave my hands in a more final sense by going to a conclusion slide. So I've tried to put forward to you Szemeredis' theorem as a case of a deep theorem. and I tried to articulate 4 different accounts of its depth that I thought had pros and cons. And I like this notion of cosmological depth. It just seems interesting to me and promising in a way that none of the other accounts strikes me as particularly interesting or promising. And then I finally just want to say that I thought that this area of arithmetic combinatorics is a nice area for thinking about depth because the theorems tend to be pretty simple to state. Like, I mean, I trust that many of you at least get what Szemeredis theorem says now. And that's amazing, right? That's a Fields Medal prize right there for proving that theorem. And yet, you don't need to know a whole bunch of crazy stuff to state this. No class field theory or characters or anything like that. Stuff that I don't really, those are hard to know, right? But this, you know what the natural numbers are? Yeah, you pretty much know what Szemeredis theorem says. But it's still a really strong theorem. And it's also an area where there's been a great deal of activity in recent decades. So you'll find articulate mathematicians telling you about what's deep about it. And that's always a good help for a philosopher. Even though we never should take their word for granted, they at least give us signposts as philosophers for what we might try to single out in our conceptual analyses. So that's the deal.
All right, we've got about 15 minutes for discussion. Professor Arana's presentation, and he'll be fielding his own questions.
Yeah, I like the idea about order out of chaos, but I'm wondering the idea that you measure the order of the premises and then the order of the conclusion. Is it? I can think there are certain theorems that tell you. You start out with something that looks like it's pretty orderly, and then it turns out that you've proved that in fact it's a matrix, right? That's all sorts of things. Like everything that's ever proven about the lattice of RE degrees.
Okay, good, yeah.
Seems to be this form, right? Where you say, you describe something that seems, okay, you have the following relations, and it looks pretty simple. And then you have this really simple lattice cannot be embedded into it, right? How many theorems are there of that type in, RE degrees in particular?
A lot.
Yeah, I mean, as I say, it seems like virtually every one. And so you say, well, look, this, at least maybe taken collectively, or at least some of these don't seem on their face that they should be ruled out as candidates for being deep, and yet they are exactly the opposite order from the one you're describing.
Yeah.
You start out with order, and then you get chaos.
That's true. I mean, I could try to fight and just say that in fact that's not deep mathematics, and that's why that area has come to a stop in the last decade or more. But rather than take that kind of...
it could be that the existence of all the chaos may have something to do with why the...
Well, I think that's true. I mean, I remember hearing that once we got to triple jump argument, no, more than that, like quadruple jump arguments, the recursion theorists were just like, man, this is not worth it. This is really hard. So Sean's advisor, Peter Cholak, was left as the main person who was doing that because all the other mathematicians were like, the recursion theorists like, we don't want to mess with this. This is just boring at this point. These arguments are too complicated.
Okay, well,
I'm just being a jerk. Yeah.
This is true.
No, but I take,
agree with all these things.
Yeah. But I take the point.
That just happened to be the example that came to mind.
Yeah. I'm sure that there's others of that type.
Others.
Well, I mean, one answer is just to say that, well, here's just a criterion of depth. I'm not sure that there is a single phenomenon that mathematicians have in mind. It may be that, like a lot of aesthetic terms in mathematics, articulateness is a kind of funny thing in mathematics. They have these terms, and as I was trying to say yesterday, they learn them in practice. We learn them as students. But we're not told the extension of these concepts. We sort of learn informally how to use them. And that context can vary quite a bit from school to school. And so I want to say that if this doesn't work out as the definition of depth, okay.
No,
Yeah.
I certainly agree that this is a nice idea which captures a lot of compelling cases.
For maybe just in the cases of like additive combinatorics, yeah. Mm-hmm.
I was thinking about what you said here toward the end. You started to talk about deeper theorems and no deepest theorem, right? And I think
Yeah.
This idea that depth is actually graded, right? It's not precisely delineated binary, deep or not deep.
Yeah.
That might help actually resist some of the complaints you had against the evidentialist type of account, because I'm very attracted to that kind of view that it has something to do with the epistemology what we learn in the process of proving and so on. That's where the depth lies. And a lot of the stuff you were pointing out here is, well, there's a lot of cases that has one of these criteria and not the other, and so on. But
Yeah.
if depth is graded, then that's just a matter of, you know, if you have one of these things, you're deeper. If you have more of them, you're even deeper.
Right.
Maybe that's okay. That's how depth works.
Yeah, that's true. You could somehow keep score, right? Like, well, this proof has this and this and this feature, and therefore it adds up to being, you know, depth grade 25. That's deeper than the one that has. So I guess it's not so different in a way than the talk yesterday of number of layers of concepts, but now we're talking about something like features of depthness of proof. So provided you have an account of depth of proof, then you could use that too. I don't have an account of depth of proof, but we do have, again, indicators. Yes, sir.
Would you agree that classification proofs could be judged by the cosmological view as quite deep?
Yeah, that's actually a good point. For all of my jerkiness about combinatorial or classification proofs so far, maybe you're right, that they show us that within the, you know, finite simple groups, right, what a mess, but not maybe as much of a mess as you could have feared. That's a good point. Yeah. No, that's a nice observation. I hadn't even thought of that. Mark, you have a point, yeah.
You were asked along the way, and thanks for letting us jump into your talk, it was helpful.
Yeah.
You were asked along the way whether any of the proofs of this theorem have been regarded as insightful.
Yes, yes.
What is it about the one to which you referred,
The Furstenberg proof,
in
yeah.
virtue of which it's been regarded as insightful?
Well, so I think the idea is just that, so ergodic theory is a way of trying to manage very chaotic objects and as it were to look for order in very chaotic situations. And I guess the thought is that Szemeredis' theorem, in a way, it incorporates the cosmological insight that an ergodic theoretic proof is able to deal with the randomness of the phenomena in a stable way. So Tao has recently observed that there's a perspective from which all three of the types of proofs that we have at present, so the combinatorial proof, ergodic theoretic proof, and the Fourier analytic proof, that they all are actually the same proof in a sense that he gets at. And you know, again, I'm very worried about individuation of proof, but he gives a compelling case that what they're trying to do is balance, as you'd expect, they're trying to balance the amount of randomness that you have in these subsets of the natural numbers. And they're trying to siphon out from that the relevant structure. So what all the proofs do are they build other structures that they can then pull out sort of the random pieces from and leave the random mess. They pull out pieces that are orderly, and then they leave the rest of the mess. And all three of the proofs employ techniques that can be seen to be doing that. The regularity theorem is, in the combinatorial case, is the means by which you pull out stuff. There are various Fourier analytic techniques that do the same thing. And then the ergodic theory way, I guess, makes it the most patently clear. Or so they say. I'm by no means an expert.
Part of the reason I was asking is because
Yeah.
There seem to be a lot of examples in mathematics where a theorem finds, broadly speaking, order in chaos.
Yeah.
And
Yeah.
it seems like in a lot of those cases, when one is looking for an insightful proof, one is looking for a proof that reveals that, in fact, the seemingly chaotic setup wasn't nearly as chaotic as you thought
Yeah.
when you were asking for an explanation of the theorem.
Yeah.
I mean, the example that comes to my mind most quickly is a much more elementary
Mhm.
example than this one. It's Morley's miracle,
Uh-huh.
where you've got whatever it is, the trisectors of an angle of any triangle, no matter how crazily ugly the triangle might be. When you find the intersections of the trisectors, the three intersection points themselves form an equilateral triangle.
Mm-hmm.
So you would have this beautiful order, as it were, buried within quite an unconstrained setup.
Mm-hmm. Mm-hmm.
And when people point out, this is miraculous, I mean, there are a lot of sort of M-related things you can say about Morley's theorem, but the fact that it's miraculous leads people to look for a proof that identifies some kind of nascent order in the setup.
Right. Right.
I was wondering whether the same kind of insightfulness is what people are looking for.
That's-
The ergodic theorem proof here is insightful.
I think so, and that's what I'm trying to single out by this criterion of cosmological depth. And it may be that if we were to try to work this out a little bit more carefully, this account, that looking at the ergodic theoretic proof would be just the way to go, to try to get at the sense in which the premises are much less orderly than the conclusion is, and to see, and to answer your question, to see why that is. So what is it about the premises that hides the latent structure? I would like to avoid as much epistemic talk as possible, even if in the end that's the only way to go.
Okay.
Sorry, yeah, Jeremy, or actually both Jeremys, yeah.
So it seems like your cosmological criterion could be spun as a kind of surprisingness.
Mm-hmm.
And I wonder why you don't just think of it as a kind of surprisingness.
Just because I was trying to avoid the subjectivity there.
So let me add a case to see what you have to say about this. So I'm trying to think through some of the other cases that people have considered as deep to see if they fit this. And in particular, the one that almost everyone has pointed to is Gödel's theorem.
Yeah.
And Gödel's theorem doesn't seem to me like it's finding order where you wouldn't think it. It's finding disorder where you would have thought there was order. And I think what's clear about Gödel's theorem is that it's surprising.
Yes.
Very surprising.
Yeah.
And you would think that if you were just going to subsume your cosmological notion under a larger notion of surprisingness, it would fit more cases. And I'm wondering if you have anything to say about, besides just I don't want to do epistemic stuff, or anything specific to say about Gödel's theorem.
Yeah, so again, the reason I was worried about epistemics, well, it's the usual situation in the kind of philosophy of math I do. I'm sensitive, as many of us are, to accusations that this is merely psychological. So one of the reasons to avoid epistemic accounts is to try to avoid those accusations. So maybe someday we'll be over that, but in the meantime, I'm not. In the case of Gödel's theorem, so I'm not so sure anything about that, about whether you'd want to say that it doesn't reveal order. Right, so the consequence tells you that you know a lot more about the structure of models of arithmetic once you know the incompleteness theorem, right? So you think of these models as walking you through trees, and you know more about what which paths work well and which paths don't. So if I think of it just in terms of walking through, so I think of something like the low basis theorem. I'm thinking of Gödel's theorem as a way to just walk through trees better.
Well,
and so
it might also be sort of a superficial deep thing where you could say, well, fixed point theorem, right? The diagonal line.
Good.
That gives you a spectacular piece of order in chaos, right?
Yeah.
You think that there's always going to be a fixed point.
Yeah.
For these, where in a case where you would think you could basically have a free hand to ruin fixed points anywhere. And it turns out that the Gödel theorem then is a kind of quick consequence of that.
Yeah.
Right, but you might say, well, it's true that at superficial level it looks like you're increasing the disorder, but when you appreciate how that's done, it turns out that there's this fundamental fact. I mean, that's just a point about the example. Because I was thinking, what about the fact that basically that the continuum hypothesis is about as false as it could be, in the sense that basically that 2 to the aleph naught could be essentially any non-singular cardinal. Is that not, that sort of seems to suggest that there's much more chaos than you would expect, but it seems like a pretty deep result.
Well, that's right. I suppose that's one reason why a certain kind of mathematician doesn't want to talk about the continuum, right? I mean, someone like Saul Pfefferman thinks that there's no determinate concept there, and a great deal of analysis in the last 30 years or so has been exactly an attempt to avoid thinking about anything but like piecewise continuous functions
then
on.
Sort of you frame it as so understood it's a proof that there is no such thing as the continuum, or that seems like, boy, describe the continuum. It seems like
it's so wild that it's not something we want to think about.
Yeah.
I mean, the case of Gödel's theorem is interesting. Also, it's funny because the recursion theorem, or I guess the fixed point theorem, isn't what I find so deep about that theorem. I find the representability of provability within arithmetic. To me, that's the wow, Gödel.
Representability is very cool.
Yeah.
No question about that.
That to me, I mean, the fixed point theorem is cool, but the amazing thing is that he got this coding to work well.
Okay.
But I'm not sure what that.
They're both very cool. I happen to have a crush on the fixed point theorem.
Yeah. You could.
But I can understand.
We can love her for the same person for different reasons. She's got a lot of appeal. Kat, you had
It's
a, oh,
actually about time for us to take our,
Okay.
our break. We'll have plenty of time for discussion a little bit later.